Once again, thank you so much to all of you for joining this second session of this 2 days hands-on training on this NanoDCAL software. So in the first session, you have get this brief idea about this NanoDCAL software and the device studio interface. So this session I will cover and where I will do the hands-on. So in the same way, you can follow the same procedure to that I will show during the demonstration. So in this C drive, you can see, and this is device studio application folder, and this is the interface for this NanoDCAL software. So this device studio will help you to model the structure. You can do some modification, manipulation in your atomic structure, device structure, crystal structure as well. So this is the device studio folder, and here you can see this is the bin folder, and here you can see this is the device studio application file. So this file you need to open. So for opening the software, you can go to the C drive. This is the device studio folder. This is the bin folder, and this is the device studio application file. So you need to open this file. So double click and then it will be open. So this is the device studio interface. So I would like to start from this scratch. So you can select this create a new project. Then you can click on this OK. And here you can enter the project name, and then you can select the location where you want to save the project. So once you enter the project name, then you can click on this save option. So this device studio is basically a graphical user interface, and this NanoDCAL is basically a background simulation engine. In the left side, you can see this is the project explorer where the input and output file will be shown. And this is the properties explorer where the property of our whole structure or individual atom you can see. And this is the job manager. So in the top up you can see this is the menu bar where the file option, edit option, view option, build option, simulator, windows and help option are there. So in the file option you can see this is for creating a new project. You can open your existing project, you can save the project, you can design your new device structure, crystal structure, molecule structure, and this is the import option. So this software have two options to import the material. Either you can import the material from this local database that exists inside this software, or you can import the material from this online database. So if we talk about this import local, and here you can see this is the material database that exists inside this software in the device studio folder. So this is the material folder, and in the material folder you can see 0D material, 1D material, 2D material, 3D material and organic material is there. This is the 0D, some molecule, amorphous and crystalline is there. This is the 1D material where some nanotubes, different combination of Kroll vector is there. This is the 2D material, some novelty material, arsenic, bismuth, black phosphorus, and this is the graphene. This is the 3D material where conductor, insulator, layer material, magnetic material, metal oxide, novelty material and semiconductor is there. So this is the conductor, pure metals. This is the insulator. This is the layer material. This is the magnetic material. This is the metal oxide. And this is the novelty material. So in the novelty material you can see this is the prescribed material. This is the topological insulator. So this is the 3D material, and this is the semiconductor. And this is the organic materials where some crystal and molecule are there. So the conclusion is that this is the material database that exists inside this software. So either you can import the material from this database, or if the material is not present here, so you can go to the import online option, file option, select import, then select this import online. and here you can enter the chemical formula, like this is the MOS2, and then you can search, and here you can see this is the MOS2 with different combination, and here you can see this is the various space group. So as per your need you can select the materials, and then you can select this add option, then it will be loaded in your dashboard. So in this session you can do this same procedure that I will show. So first I would like to calculate some material properties from this NanoDCAL software. So you can select any materials from the local database, or either you can import from this online database. Or if you want to create a new crystal structure, molecule structure, then you can select this new option, then you can do like crystal builder. So this is the crystal builder where you will find various space group, and this is the previous lattice. So this previous lattice will selected once you select the space group, and also you can change their ABC value, alpha beta gamma value. You can add the element from this plus option, like that. Like here you can see this is the default carbon atom, but if you want to change this carbon with another atom, so from periodic table you can select any element, like this is the silicon. Okay, and then you can show their primitive cells, conventional cells, then you can preview, then you can build. So either simple structure, complex structure, alloy, any type of crystal builder you can build from this crystal builder. So for simulating the material, first I would like to import some material from the local database. So you can select this file option, select this import option, select this import local. So you can go to this file option, select this import local, and go to this C drive, device studio, then open this material folder, and you can select any materials, like this is the 3D materials, semiconductor, and here you can see this is the silicon. So you can select this silicon from this local database, then you can select this open option. So here you can see this is the silicon that I have imported from my local database. So I hope everyone has been imported this silicon from the local database. So for importing this silicon, select this file option, select this import option, go to this import local, go to the C drive, select this device studio, select this material, select this 3D materials, select semiconductor, and here you can see this is the silicon. You can select, then you can open. And for simulating this silicon structure, you can select simulator, and in this simulator you will find multiple options, like this is the NanoDCAL for the DFT and NEGF method, and this is the nano scheme for the nano structure for the tight bonding model, and this is the rescue for the DFT and DFPT solver, and this is the rescue plus, that is the advanced version of this rescue. So you can select simulator, select this NanoDCAL, and in the NanoDCAL you will find multiple options, like this is the virtual crystal approximation, this is the self-consistent field calculation. If you want to do the optimization, so this is the relax option, and this is the analysis option. So this is the virtual crystal approximation for the doping, like either you can import n-type doping, p-type doping. So doping is also possible. So first you can select simulator, select NanoDCAL, then you can generate their SCF calculation from this SCF calculation. So here you can see this is the SCF calculation for this crystal, silicon crystal structure, and this is the basic settings. where you can see this is the electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K-point sampling. This is the iteration control, where you can see density matrix, Hamilton matrix, total energy. This is the basic set, where you can see this is the arrangement by element by atoms, and this is the LDA plus U, that is the Howard atoms. In the atom you can see this is the silicon, and this is the LDA double zeta polarized, their neutral atomic database. And this is the spin type calculation. So if you want to include the spintronics application in your silicon structure, then you can select this spin type, select this no spin, then you will find this collinear spin, general spin. So as per your need you can define the input parameter, and then you can generate their input file. So this is the basic settings, iteration control, basic set, spin type calculation. So in this spin type you can see collinear spin, and here you can see this is the value of spin polarization rho. And if you go this general spin, then you will find rho theta phi. And also if you want to do the spin orbital interaction, then you can select this option. So you can select this collinear spin and then generate their input file. So once you define their parameter, then you can select this generate file. So I hope everyone has been generated their scf.input file. So here you can see this is the scf.input file, and here you can see this is the properties of this silicon. Here you can see this is the vector value, vector ABC, and this is the total number of atoms, and this is the total area of this lattice. And if you want to show the property of individual atoms, so you can select, and here you can see this is the silicon and their XYZ position. So once you generate the input file, like this is the scf.input file. So if you want to show their script, so you can select this scf.input file, right click, and then select this open with. So for showing their script, you can select the file, right click, select this open with, and this is the script for this silicon crystal structure. So here you can see this is the SCF, self consistent field calculation. This is the basic settings like electron temperature, cutoff energy, exchange correlation function. This is the K-point sampling, and in this spin type you can see collinear spin is included. This is the iteration control parameters, and this is the basic settings like this is the atom, silicon, and their Cartesian coordinate point. And here you can see this is the value of spin polarization. So there is no need to write the script. So once you define their parameter and generate the file, then their script will automatically generate it. And for running this scf.input file, you can select the file, right click, then you can select this run option. So for running this scf.input file, select the file, right click, select this run option, and here you can select this run option to run this job. So in the bottom of the page you can see this is the job manager, where my scf.input file is in the running condition. So once you run the scf.input file, so you need to generate the analysis input file. So for the analysis, you can select simulator, select this NanoDCAL, then select this analysis. So for selecting the analysis input file, you can go to the simulator, select this NanoDCAL, then select this analysis. So this is the analysis input parameter, for the material simulation. Like here you can see this is the density of state, effective potential, total energy, band structure, charge, Hessian, Funan band structure, electron density, potential, trans channel, eigenstate, full band structure, effective mass, complex band structure, ZT, Funan full band structure, Funan density of state, Funan trans channel, and this is the modulus. So you can select any analysis input file. So if you want to select, so double click on the file, then it will be selected. So you can double click on the file, then it will be selected. Here you can see this is the density of state that has been selected, and this is the density of state parameters. Like this is the k point sampling, number of energy point, energy range, and this is the projection. So like projection in the sense, like here you can see this is the none option, that is for the default. Then your density of state will be plotted. And if you select this atom and orbital, then your density of state will be plotted with the atom and orbital wise. And if you select this ELL, then your density of state will be plotted with the orbital with the angular momentum. So ELL option is for the orbital with the angular momentum, and this is the atom and orbital for the density of state. So you can select any option. So I am selecting the default option, none option. And you can define some k point sampling so that your data will be plotted. So you can define n1 is equal to 3, n2 is also 3, and n3 is equal to 3. So you can define this parameter. So I hope everyone is doing the same procedure that I am showing. Like this is the density of state, and if you want to select this band structure, so double click, then it will be selected. And again you can select this band structure, then you will get the band structure parameters. Here you can see this is the symmetry k point, and if you want to show the Brillouin zone path, so you can select this path option, and this is the Brillouin zone path for this silicon structure. And here you can see this is the symmetry k point and their value. So this is the symmetry k point, and this is the number of k point. Similarly, if you want to select this charge option, so this is the charge. Once you select this charge option, then you will get the magnetic moment. Like here you can see this is the project option, this is the none, ELL, atom and orbital. This is the Hessian. So this is the Hessian matrix. This is the Funan band structure. Here you can see this is the Funan band structure parameters, symmetry k point, and this is the number of k point. This is the electron density, and in the watt density you can see this is the charge density, total electron density. So any density you can select, then you can show their plot. This is the potential. In the watt potential you can see this is the effective potential, Hartree potential, exchange correlation potential, and this is the neutral atom potential. And this is the trans channel, and here you can see this is the trans channel parameters. This is the eigenstate. Here you can see this is the k space point, n1, n2, n3, and this is the number of band. This is the effective mass. Here you can see this is the hole and electrons, and this is the value of -1 is for the second conduction valence band, and 1 is for the valence band. And if you select -2, so this is 1 for the conduction band, first conduction band, and the -1 is for the second conduction band. And if you select this -2, so this value is for the second valence band, and this value is for the second conduction band. And here you can see this is the spin value, spin up, spin down. 1 is for the spin up, 2 is for the spin down. And here you can see this is the K point sampling. This is the complex band structure. Here you can see this is the complex band structure parameters. K space grid number, number of energy point, energy range. So you can select multiple analysis input and then you can generate their input file. So after selecting the input file, you can select this generate file. Then their input file will be generated. Here you can see the SF input file has been completed. Here you can see this is the time taken by this software, 2 minutes 12 seconds. And here you can see this is the step-wise step procedure for calculating the parameters. So in the same way you can run all the analysis input file. Like this is the density of state. So for running this input file, you can select the file, right click and select this run option. So for running the input file, you can select the file, right click, select this run option, and here you can select this run option to run this job. Here you can see in this density of state.input file is in the running condition. So in the meantime, you can run all the analysis input file in the queue condition. Like this is the band structure. This is the charge. This is the Hessian. This is the phonon band structure. This is the electron density. This is the electron density. This is the potential. This is the trans channel. This is the eigenstate. And this is the effective mass. This is the complex band structure. So here you can see in the job manager, you can see I have run all the input file in the queue condition. Like when this Hessian.input file will finish, then this phonon band structure will start automatically. So once this file will finish, then their output will definitely generated. So I hope everyone has been run their input file, and some of the input file, here you can see some of the input file has been completed and their output has been generated. So you can wait till then our output will be generated. So during running the any input file, if you are getting any problem, any errors, so if you are getting any error while running the any input file, so kindly let me know so that I will help you, or you can drop the message in the WhatsApp group so that my team will be helpful. So once your simulation finished, you will get the output. Like here you can see my density of state simulation has been completed and their output has been generated. So this is the density of state.xml file. So this is the output file and this is the input file. So for showing the output file, you can select the file, right click, select this show view. So for showing the output file, so you can select the file, right click, first you can select the file, right click, select this show view, and you can show this is the density of state with respect to energy. And as you know, we have defined some collinear spin in our input file. So here you can see this is the spin up. So this is the spin type, this is the spin up, this is the spin down. So this is the spin down graph, this is the spin up graph, this is the spin down, and this is the both spin up and spin down. So for showing the manual, you can visit our official website nanoacademic.com and go to the bottom of the page. You will find this document and tutorials. You can select this NanoDCAL. So here you can see this is the theory and this is the tutorials. And for the input reference, you can select this calculator parameters. Then you select any option. Like here you can see this is the for the density of state, and what parameter you need to select. Here you can see all the steps are available. So this is the density of state in output file. So here you can see all the simulation has been completed and their output has been generated. This is the density of state, this is the band structure. So you can see this is the band structure for this silicon crystal structure. This is the conduction band, this is the valence band, and this is the location of Fermi energy. And in the spin type you can see this is the spin up, this is the spin down, and this is the both spin up and spin down. And you can select the location of the Fermi energy from this Fermi energy option. Here you can see this is the located on the middle of the band gap, top of the valence band, this is the bottom of the conduction band. And if you want to export or raw data, so here you can see this is the export option. Then you can select the format like PNG, JPG, BMP, PDF, text format. So any format you can select, like this is the text format. Want to export, then you can select this save option. Like here you can see this is the band structure, and this is the band structure for the spin up, and here you can see this is the band structure text file for the spin down. And some of the output graph will open in the MATLAB, like this is the charts that will open in the MATLAB. So if you want to show this charts, you can select this file, charts file, right click, select this open containing folder, And here you can see this is the charge.mat file, and this mat file you can open in the MATLAB. So if you have MATLAB, so here you can see this is the MATLAB. So from this browse option, you can locate your project into the MATLAB. Here you can see this is the location of my project, NanoDCAL hands-on. Then I would like to select this folder. And here you can see this is the silicon folder. This is the NanoDCAL crystal folder. And then you will find all the input and output file. Like here you can see this is the band structure input file. This is the band structure.mat file. This is the band structure.xml file. And here you can see charge input file. And this is the charge.mat file. So you can double click on the chart.mat file, and here you can see this chart.mat file has been loaded. Here you can type the command data. Here you can see, and this is the command for showing the output. Then you can press the enter. So you can load the input output file, like this is the chart.mat file. Double click, it will be loaded. Then you can type this command data, press the enter. Then you will find the parameters, output parameters. Like here you can see this is the value of total charge. This is the spin polarized charge, rho theta phi, and this is the spin magnetic moment. So if you want to show the description, again you type the command data dot description, press this enter. And here you can see this is the spin magnetic moment in the unit of electron volt per Tesla. So this is the value of electron volt per Tesla, 2.4237 into 10 to the power minus 12 electron volt per Tesla magnetic moment. So this is the charge file. This is the phonon band structure .xml file. So you can select the file, right click, select this show view. And this is the phonon band structure for this silicon crystal structure. This is the total electron density. So in the draw model you can see this is the 3D view. If you want to show the 2D, then you can select this 2D option. So this is the 2D total electron density for this silicon crystal structure along x-axis, y-axis, z-axis. And in the show model you can see this is the planar display, this is the stereoscopic display along x-axis, z-axis, y-axis, x-axis, and this is the 1D view along xy plane, yz plane, xz plane. So you can select any option like 3D, 2D, 1D, and then you can show their data. So this is the total electron density. This is the effective potential. Here you can see this is the 3D view. This is the 2D view along x-axis, y-axis, z-axis, planar display, stereoscopic display. and this is the 1D view. This is the transmission channel. So you can see this is the transmission channel with respect to energy, and this is for the spin up, this is for the spin down, this is for the both spin up and spin down, and this is the total transmission channel with respect to energy. This is the hygiene state. This is the 3D view. This is the 2D view. Here you can see this is the spin up, this is the spin down, and this is the 1D view. Spin up, spin down, and this is the complex band structure. Here you can see real and imaginary part is there. Red one is for the real and blue one is for the imaginary. And this is for the spin up and this is for the spin down. So I hope everyone gets their output once their simulation will finish. And if you want to simulate more properties, like here you can see, select simulator, NanoDCAL, go to the analysis, and here you can see this is the ZT. So in the ZT you need to import this primitive cell input file. Like here you can see for the system object file. Here you can press, then go to the location of your project. Here you can see this is the project, my project NanoDCAL hands-on. You can open this file, then you will get this silicon file. Again open this NanoDCAL crystal file, and then you need to import this NanoDCAL object file. You can select, then you can import. So here you can see this file has been imported, and this is the K point sampling, Q point sampling, energy range, temperature range, and this is the direction. And also if you want to calculate the modulus like Young modulus, elastic modulus, so you can select this modulus option. And if you select this VWD interaction, then the van der Waals force will be selected. Like this is the jetting, this is the modulus. You need to generate their input file. Similarly, you can run this jet input file. Again, this is the modulus input file. So for generating the jet input file, you can go to the simulator, select NanoDCAL, select this analysis, and here you can see this is the ZT. So you can double click, then it will be selected. In the primitive cells, you need to import this NanoDCAL object.mat file. So here, you can click here, then go to your project location. Like here you can see this is the location of my project. Here you can see this is my project NanoDCAL hands-on. I need to open this file, then you will find this silicon folder. Again you need to open this file, then you will find this NanoDCAL crystal folder, and this NanoDCAL object file you need to import. So you can select this file, then click on open. And once you imported this file, then go to the generate file option. So in the job menu you can see Z input file has been completed and their output has been generated. So this is the thermoelectric properties .xml file. So if you want to show their plot, so you can select the file, right click, select this show view, and here you can see this is the thermoelectric properties. This is the conductance with respect to temperature in the unit of Kelvin. And if you want to show with respect to chemical potential energy, then you can enable this option. Here you can see this is the conductance with respect to chemical potential energy in the unit of electron volt. So this is the conductance. In the plot type you can see this is the conductance. This is the Seebeck coefficient in the unit of temperature. This is the chemical potential energy. So this is the Seebeck coefficient with respect to temperature and with respect to chemical potential energy. This is the thermal conductivity for the electronics. Here you can see with respect to temperature, with respect to chemical potential energy. So this is the thermal conductivity for the temperature, with respect to temperature and with respect to chemical potential energy. So this is the with respect to electronics, and this is with respect to phononic. So this is the thermal conductivity with respect to temperature, with respect to chemical potential energy. In the plot tab you can see G is for the conductance, S is for the Seebeck. Here you can see this is the Seebeck coefficient with respect to chemical potential energy, and this is with respect to temperature. This is the conductance, Seebeck coefficient. This is the thermal conductivity with respect to electronics. This is the thermal conductivity for the phononics, and this is the ZT. Here you can see this is the temperature, and this is the chemical potential energy. So this is the thermoelectric properties, and also you can see the modulus dot input file has been completed. So this is the modulus dot input file. Select this file, right click, select this open container folder, and here you can see this is the modulus text file, output file. This is the input file, and here you can see it has generated their mat file. So for showing the output of modulus, again you need to open your MATLAB, and here you can see this is the elastic module. So this is the input file, and here you can see this is the output file. So you can double click on this modulus, elastic modulus, then it will be loaded. Again you need to write the command data, then press this enter. So here you can see this is the elastic modulus and their output file. Like here you can see this is the Younger modulus, this is the shear modulus, this is the Poisson ratio. So you can see this is the value of Younger modulus. So for Younger modulus output, you can write this command data dot Younger modulus, and for the shear modulus, again you need to write this command data dot shear modulus, then press the enter. And here you can see this is the value of Poisson ratio. And here you can see this is the effective mass dot mat file. Double click, then it will be loaded. Again you need to type this data command, then press the enter. And here you can see this is the value of effective mass. And here you can see this is the input parameters: band energy, mass longitudinal, directional longitudinal, mass transversal, direction transversal, mass transversal 2, and this is the direction transversal 2. So if you want to show the band energy, you need to write this command: data dot effective mass dot band energy, then press the enter. And here you can see this is the value of band energy. And if you want to show the mass longitudinal, then you need to write this command, then press the enter. Data dot effective mass dot mass longitudinal. So in the same way, you can find the output of every input parameters. So basically this is the material properties. So you can follow the same procedure for simulating any materials, either complex structure, alloy, simple structure. So any material structure you can simulate through this procedure. And like here you can see this is the silicon. So if you want to show their face center cubic structure, body center cubic structure, then you go to the this. So you can go to this build option. You can select this redefine crystal. So in the builder you can see multiple options are there, like this is the molecule 3D builder, this is the molecule 2D builder, and this is for the decomposition, this is the device maker, this is the convert to device option, this is the interface builder, this is the crystal builder, this is the redefined crystal. So if you want to show the face center cubic structure, body center cubic structure, then you can select this redefined crystal. Here you can see, and this is the FCC, face center cubic structure, and this is the BCC, body center cubic structure. Like this is the FCC, and this is the BCC. So either face center cubic structure, either body center cubic structure you can select. Select this preview option, then select this build option. So this is the face center cubic structure of this silicon and crystal structure. And if you want to select the surface slab, here if you want to define the Miller indices like SKL value 100, 110, 101, so any combination you can select. And if you want to include the slab, like here you can see this is the slab option. And if you want to increase the thickness, so this is the thickness option, and this is the vacuum option. So if you want to increase the thickness, so you can select this plus option, and then you can increase like that. And if you want to create a vacuum in this structure, so you can select this plus option, and you can create a vacuum like that. So any combination you can select, like this is the 100. If you select 101, here you can see this is the 101. Select this slab, increase the thickness if you want, and also if you want to increase the vacuum, so this is the vacuum option. This is the 100, and if you want to select 110, select this slab option, increase the thickness. If you want to increase the vacuum, select this plus option. So as per your research work, you can select this surface slab, and then you can build the structure. So here you can see this is the 3D viewer, where you can see XY view, XZ view, YZ view, YX view, ZX view. So any view you can select, and you can show the structure. Like this is the XY view, this is the XZ view, this is the YZ view, and this is the ZX view. So this is the surface slab with respect to 111. And if you want to select this graphene nano ribbons, nanotube, grain boundary, nanotube, nanowire, like this is the nanotube. And here you can define the crawl vector like A and an M value. So like here you can see N is equal to 5 and M is equal to 5. So this is the nanotube for this silicon structure. So either armchair, zigzag, any type of structure, nanotube structure you can create from this nanotube builder. And if you want to increase this length, here you can see this length is quite thin. So if you want to increase the length, select this build option, go to this redefine crystal, and you can redefine your crystal by expressing the new cell vector UVW as a linear combination of ABC. So this is the transport direction, that is C. Here you can see I have increased 10 times in the direction of C. Preview. So this is the silicon nanotube. And if you want to make a nanowire, so here you can see this is the nanowire, and here you can select the wire direction like 100, 110, 111. Then you can define the cluster parameter, like this is the cluster radius 7.5 angstrom. This is the surface energy for the 100. This is the surface energy for the 110. This is the surface energy for the 111. Like here you can see this is the wire, nanowire in the direction of 110. So any combination you can select. and then you can build this structure. And similarly, if you want to increase the length, select this build option, select this redefine crystal, and you can redefine in any direction, either ABC, A direction, B direction, or transport direction, that is C direction. So here you can see this is the transport direction. So this is the nanowire, this is the nanotube, and this is the graphene nano ribbons, and this is the graphene nanotubes, and this is the grain boundary. So if we talk about this grain boundary, so here you can see this is the value of sigma 3, 5, 7, any value you can select, and this is the axis, this is the value of theta, and this is the cos theta. And here you can see this is the grain boundary plane, scale value. So any grain boundary plane you can select, and then you can show their structure. Like here you can see, and here you can see this is the disorder graphene like structure, this is the disorder zinc blend like structure. So here you can see this is the graphene, and this is the carbon atoms on the side A, on the side B you can see carbon atoms, and this is the bond length, and this is the value of supercell. N1 is equal to 10, N2 is equal to 10. So if you want to increase this value, like this is the 20, and this is also 20. So this is the graphene like structure. So if you want to make a boron nitride based structure, so on the site A you can change this carbon with the boron, and on the site B you can select this carbon with the nitrogen. So for changing this carbon, double click on this carbon, and from periodic table you can select this boron. Similarly you can select this second carbon, this is the boron. Okay, so on the site A you can see this is the boron, and on the site B you need to select this nitrogen. So here you can see this is the boron and this is the nitrogen, and if you want to increase the bond length, so here you can see this is the boron nitride, and then you can select this field option. So here you can see all the result is for the single silicon structure. So if you want to expand any structure, like this is the nanowire, if you want to expand this structure, so you can select this build option, select this redefine crystal, and then you can choose the direction where you want to expand, like this is the A direction, B direction, C direction. So in any direction you can increase like that. So if you want to increase in the direction of A as well, so you can increase. Here you can see. So in any direction you can select, and then you can preview, then you can build. So this is the disorder graphene like structure, and this is the disorder zinc blend like structure. So if you want to change this carbon with another atoms, then double click on the carbon, then periodic table will open. So from periodic table you can select any element, like this is the aluminum, click on OK, then it will be selected. So this is the zinc blend like structure. Preview. This is the bond length, this is the superset N1, N2, N3, and this is the build option. And here you can see this is the MOS2. So if you want to delete any atoms, so you can draw the rectangle, select the atoms, then it will be selected, then you can press this delete atoms. So if you want to delete any atoms, draw the rectangle, select the atoms, then press this delete atoms. So this is the MOS2. So if you want to do the optimization, so for optimizing the structure, you can select simulator, select this NanoDCAL, then go to the relax option. So for optimizing the structure, you can select simulator, select this NanoDCAL, then go to this relax option. Here you can see this is the basic settings: electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K point sampling, and here you can see this is the relax option. In the method you can see this is the molecular dynamic, and this is the CG for the conjugate gradient. So any method you can select, either molecular dynamic, either conjugate gradient, and then you can generate their input file. So after defining all the parameters, you can select the method MDRCG, then you can generate their input file. Also you can see this is the force convergence criteria. So you can define as per your research work, select the methods, generate the input file. So once you generate the file, in the project explorer you can see the relax.input file has been generated. So this is the relax.input file. So if you want to show the relax.input file script, select the file, right click, select this open with. Here you can see this is the relax parameters. In the method you can see this is the molecular dynamic, this is the force convergence criteria, and here you can see this is the relaxation fixed central cell 1 2 3, and this is the basic settings: electron temperature, cutoff energy, exchange correlation function, LDA. This is the K point sampling, no spin is included. This is the iteration control. This is the atom and their Cartesian coordinate point. So for doing the optimization, first you can generate the first you can create the crystal structure, molecule structure, any structure you can create. Go to the simulator, select nanodical, then go to this relax option. Here you can define the parameters. This is the relax option. In the method you can select anyone, either molecular dynamic or conjugate gradient. So any method you can select, then you can click on this generate file. And once you click the generate files, in the project explorer you will find the relax.input file. And for running, so you can select the file, right click, select this run option, and here you can select this run option to run this job. In the job manager you can see the relax.input file is in the running condition. So in the log.text file you will show the procedure of simulation. Like here you can see, this is the input file, relax.input file, and here you can see, and this is for the starting the calculation. This is the molecular dynamics method. Here you can see total number of electrons in the central cell is 24 and in the basic cell is 44, and this is the 2D periodic and no spin is included. And here you can see total number of atom is 3, and here you can see the structure is getting relaxed. Like here you can see this is the step first, this is the step 0. First it is calculating the forces. Here you can see 36 seconds, and here you can see maximum atomic forces 2.312 electron volt per angstrom, and this is the maximum atomic force for the step 0. And also you can see the simulation is ongoing. So once this simulation will finished, then you will get a input file for the optimization. MO2S4 input file you will get. So until the simulation is running, so I can show you the more features of this software. So in the build option you can see, so if you want to create an interface, like here you can see this is the interface builder. So first you need to select the structure. Here you can see this is the structure A, structure B. So I need to import some material. Like here you can see this is the gold. This is the gold. And if you want to import the 3D conductors, and here you can see this is the silver. So this is the silver crystal structure and this is the gold crystal structure. So this is the single gold and this is the single silver. And if you want to make an interface between these two, gold and silver, select this build option, go to the interface builder. In the structure A, you can select the, like here you can see this is the gold. In the structure B, you can select this silver. First you need to match and then preview. So this is the interface between these two, gold and silver. So if you want to increase the number of atoms, so here you can see total number of atoms is 16. So if you want to increase, like here you can see total number of atoms is 102. And also you can see this is the angle, rotation, mismatching, area, strain. So this is the interface between this gold and silver crystal structure, and then you can build this structure. In the job manager you can see the relax.input file has been completed, and it has generated input file like atom.relax xyz. Like here you can see this is the mo2s4 structure that I have imported from online database, and it has after relaxation it has generated one more file, atom relax.xyz. So you can select this file option, select import option, select this import local, and then you can choose the location of your project. Like here you can see this is my project nanodical hands-on, and here you can see this is the mo2s4 file, this is the nanodical crystal file, and this is the atom relax.xyz file. So you can import this file, and then you can do the simulation. So first I need to import this file, open. So here you can see this is the structure, and this is the relax structure. I think there is some minor differences there in it. Like here you can see. So this is the relaxed structure, and then you can do the simulation. Again you can generate the RSF input file. You can define your own parameter as per your need. Generate the file, and then you need to run the file. In the relax file you can see it has taken 13 steps to relax the structure. You can see this is the step 0 and the maximum atomic forces, and this is the step 1 and their maximum atomic forces, and this is the step 2 atomic maximum atomic forces, and this is the final maximum atomic forces. Here you can see 0.027 electron volt per angstrom, and it has taken 5 minutes 6 seconds. And this is the band structure for the relax EMO2 structure. And if we talk about this molecule 3D builder and molecule 2D builder, so here you can see this is the molecule 2D builder, and this molecule 2D builder will help you to model the molecule. So either simple molecule structure, complex molecule structure, you can build from this molecular builder. In the left side you can see various fragmentation are there. So as per your need you can select the fragmentation. Like here you can see this is the ring segment. So if you want to design a benzene structure, so you can select this ring segment. And as you know in the benzene there is some hydrogen atom is there. So first I would like to create a single bond. This is the single bond. This is the double bond. This is the triple bond. So I am selecting this single bond, and you can select like that. But as you know, in the benzene structure there is only hydrogen atom, so I need to change this CH3 with the hydrogen. So again, you can select this choose element, select this hydrogen, cancel, then you can press here. So this is the benzene structure C6CH6. And once your structure is ready, then you can select this apply data. So here you can see this is the benzene structure, and in the toolbar you can see this is the force field calculation like UFF, GFF, chemical. So any force field calculation you can select, like this is the GFF and this is the structure. So as per your need you can select the force field calculation, then you can do the simulation. So this is the molecule 2D builder, and if we talk about this molecule 3D builder, so this is the molecule 3D builder. And if you want to add the element, so here you can see this is the add option. So from periodic table you can select any element, like this is the carbon, and there are various fragmentation, like this is the single atoms, this is the divalent, this is the divalent with respect to DD, this is the trivalent, and this is the tetrahedral. So any option you can select, then you can press anywhere. Or if you want to import this molecule, so this option is also available. Select this file option, select this import option, and here you can see this is the molecule, benzene molecule. So if you want to make a trinitrotoluene structure, so you can go to this add option, select this carbon atoms, select this single atoms, and you can change this hydrogen with the carbon. Again select this hydrogen, like here you can see this is the add hydrogen option, and you can press 3 times. So this is the toluene molecule, and if you want to make a trinitrotoluene structure, so you need to add the nitrogen group. So here you can see this is the add option, select this nitrogen option, select this single atoms, and you need to change this hydrogen with the nitrogen. This one is also, this one is also. So this is the nitrogen, and for the nitrogen group I need to import some oxygen. So first I am generating some hydrogen atoms, and then I can change this hydrogen with the oxygen. Select this add atom option, select this oxygen, select single atoms, and here you can see hydrogen has been replaced with the oxygen. So this is the trinitrotoluene structure. And once you build the structure, then you select this apply data. In the toolbar you can see, and this is the modify bond. So if you want to modify the bond between two atoms, select this modify bond, select the atoms, Here you can see this is the single bond, this is the double bond, this is the triple bond, this is the resonance bond, and this is the half metallic bond. So as per your need you can select the bond, and then you can select this OK option. And here you can see this is the modify angle. So you can modify the angle between the three atoms. So you can select the atoms, so either you can put the angle value here, from this option you can change like that. And if you want to fix this first atom, second atom, so here you can see this is the atom first, this is fixed, then only 2 and 3 will be rotate. Here you can see. And if you want to fix this second, so only third atom will be rotate. So as per your need you can select, and then you can click on this OK. So this is the 246 trinitrotoluene molecular structure. Then you can select this supply data. So this is the benzene molecular structure, and this is the 246 trinitrotoluene structure. And this new device builder I will show you tomorrow. So tomorrow's session will based on this device simulation. So how you can select their like input file for the device, electrode, you can define some electrode. So tomorrow's session is based on this device simulation. And here you can see this is the single layer boron nitride structure. So if you want to make a multi-layer structure, select all the ones. And here you can see you can define this on normal vector xyz, like xy, xz, yz, any position you can select. Like this is the xy. Copy this checkbox, then apply. So here you can see in the xy direction one more layer is created. So if you want to increase the distance, here you can see this is the normal vector xy, and this is the distance, and then you can copy this checkbox, then apply. And if you want to make it centrally fit, this is the center option. So here you can see this is the double layer boron nitride structure. So either single layer, double layer, triple layer, so multiple layer structure you can create from this mirror atoms. So I want to conclude this session because I have shown you some maximum features of the material simulation, and tomorrow's session I will cover on the device simulation. So if anyone has any query related to the material simulation, so you can unmute your mic or you can drop the message on the chat box so that I can reply. So for the biomedical science, like so in this device structure you can see this is the molecule 3D builder, and some biomolecule is there. You can see this is the biofragmentation. In the type you can select anyone, you can select like acetylene group, any group you can select, like this is the uridine, and then you can find their structure. Like here you can see. So here you can see various biomolecule structure are there. Like here you can see. So this is the biofragment. So you can select anywhere, and here you can see this is the R group. So this software is also very useful for the biomedical science, because some of the biomolecular structure are there. Biomolecular structure. So any structure you can select, you can press anywhere, and then you can select their apply data, and then you can do the simulation. So either from this simulator nanodical rescue, you can simulate the structure. And if you want to show any some publication papers, so you can visit Google Scholar page, where many of the paper published in many domains. So either spintronics, semiconductor, molecular science, biomedical science. So here you can see various publication papers are there. Here you can see, and this is the biomedical applications, and here nanodical has been used. So if you want, so I can send you these papers to you. So I will share this paper to you so that you can check. So thank you so much to all of you for joining this session.